Hi folks, in this video we're going to have a look at the way in which we can multiply and divide complex numbers in polar form. Now what we're going to do here is we're going to follow through a proof for both the product and quotient of complex numbers in polar form. Now this does require the use of what's called some trig identities. Now back on this page here in the content library, where this video link can be found, the trig identities that we're going to be using are these ones here. Now the proof of most of these ones here we will look at later in the year when we do some work on trigonometry. Now if you're really eager to look at the proof of what are called the compound angle identities, these are the ones I'm highlighting here at the moment, they can be found in the content library here. Okay, there's a bit of work there that proves those trig identities. This other one here, we'll simply wait until later in the year to prove this one. Now for the moment then we're going to take it, assume that these things are true. So using those trig identities, let's then move right into having a look at the proof first of all of when we're multiplying a couple of complex numbers in polar form. So let's just call this A, and this is when we're multiplying. So multiplying what? Well, let's take a complex number, let's call it Z, and let's say we've got R1 cis A. Now just a reminder that in polar form, which is what this is called the moduli, or modulus I should say, and this angle here A is called the argument. So an example of that would be something like Z is equal to 2 cis, say, pi over 4, where this angle at the moment is in radians. Okay, so moving back here, let's say we had a different complex number, let's call it W, and let's say that the modulus was R2 and the argument angle B. Don't really need to put that in brackets, but I will for now. Okay, so what we're going to have a look at then is what would this look like if we were to multiply the two complex numbers in polar form. So Z times W, what would that look like? Well, I think it stands to reason that would have R1 cis A times R2 cis B. Now, a reminder that this CIS is simply shorthand for what I'm about to write as follows. I'm just going to move this up a little bit, just making it easier to write on my tablet here. Okay, so let's continue working down here. So this would be R1. Now CISA is short for excuse me, the cosine of A plus I times the sine of A, I sine A, and I'm going to multiply that by this other complex number, which I'm also going to write out in full form. And that's a B. Now we're multiplying R1 times the bracket times R2 times this other bracket. Now when you multiply things together, you can multiply them in any order. So I'm going to move R1 times R2 to the front here, and then let's have these brackets. And what we're going to do in a moment is we're going to multiply the brackets out. I'm just going to move things up a little bit as I go. It's just a lot easier to write on this tablet if I have it at the top of the screen here. So R1, R2. Now let's put a big bracket. I'm going to multiply cosine A times cosine B, cos A, cos B, cosine A times I sine B. So that would be cosine A sine B I, and then I sine A times cos B. Let's put that as sine A cosine B I, and then we've got I sine A times I sine B. That would be I squared sine A sine B. Okay, let's see if we can make something more of this. Now what I'm going to do is I'm going to group the real and imaginary parts separately. So this is a real part here, the cosine A cosine B. Now I squared, you might recall, is equal to -1. So that is therefore going to be minus sine A sine B, and it will be a real part. So let's put that here. Oops, don't want to put a bracket yet. Let's make that eraser a bit smaller. Okay, plus, now I, let's take I out as a common factor of these two middle terms here, and a bracket, cosine A sine B plus sine A cosine B, big bracket. Okay, now if we didn't use any trig identities, we'd basically be stuck here at this stage. But just jumping back to the trig identities for a moment, and I'll just copy them and put them underneath here so we can refer to them. Okay, let's take these identities here and put them on this page. Let's put them down there. Now let's have a look at these down here at these identities. Which one can we use? Well, if you look at the cos A cos B, that looks like one of these third identities, the minus sine A sine B. Now what's this minus plus and plus minus business? Well, what we have here is a minus sign between the cosine A cosine B and the sine A sine B, so it matches that top line, the top part. So cos A cos B minus sine A sine B, and that would equal this left hand side here where we've got the plus sign, so that's equal to cos bracket A plus B. So all of this, the first part here, can be replaced with cos A plus B and plus I. Now what about this part here? Well, if we have a look at that, we've got cos A sine B, so cos A sine B plus sine A cos B. Now okay, we're adding and it's the opposite order here, but when you add two things the order doesn't matter. So basically we've got that top line here, we've got cos A sine B added to sine A cos B, so that would equal sine A plus B. So I'm going to put that in place of this here. So what we're saying is that all of this part here can be replaced with this here. Okay, that's using this third identity down here, and all of this part here, okay, using this second identity here, can be replaced with sine A plus B. Okay, well, think, well, so what? That's all very nice, I'm sure, but how can we use that? Well, what you've got here is you've got basically a complex number in expanded polar form, and what that number is is R1 times R2, which is simply a number, the product of the two moduli, and we've got cos A plus B plus I sine A plus B. Well, that can be written as CIS A plus B. So what does that mean? It means that, just scroll back up for a moment, if we've got two complex numbers in polar form and we want to multiply them, well, the quick way of doing that, what this end result tells us, is we simply multiply the two moduluses together, which is called moduli for plural, and these arguments are simply being added. So we multiply the moduli and add the arguments. So let's have a quick look at a single example of that. I think I will do that over here on the right hand side. So let's take a look at an example. Oops, getting a bit too messy. So let's take this one that we had a moment ago, 2CIS pi over 4, and let's say we had W equal to, let's say, root 7 CIS pi over 3. That's a 4 there. Okay, so what would Z times W equal? Well, according to this end result, we simply multiply the two moduli, so 2 times root 7 to root 7, and the arguments we're going to add, so pi over 4 plus pi over 3, and that is something we can simplify. Okay, so the common denominator would be out of 12, and so you'd end up with 3 pi plus 4 pi over 12, which of course would give it as 7 pi over 12, which is the end result. Okay, so a quick way then of multiplying when you've got complex numbers in polar form: we multiply the moduli, add the arguments. Okay, so what about division? Okay, so what I'm going to do is simply move right down further down the page here. Okay, try and keep those trig identities somewhere where we can see them. I'm just going to move them over to the right here. Okay, and let me scroll that up a bit. Not that far. Sorry, mucking around here a bit. Okay, and let's get rid of that asterisk for now. Okay, let's go back to, okay, let's swap to green color here. So let's say we're trying to divide. Okay, so we're finding the quotient. Quotient means to divide. Okay, this is a little more involved, and we're going to have to do some rationalizing of denominators, but let's go straight into it. So we've got Z over W. Z was R1 cis A over R2 CIS or cis B. Let's write that in expanded form. Cosine A, sorry, it's getting too messy. Plus I times the sine of A. And this is cosine B plus I times the sine of B. Okay, now to do anything with that, we're going to have to take the R1, R2 and just leave that out the front, and then I'm going to take this complex number essentially, and I'm going to rationalize the denominator. Now I'm just going to pause the video just a little bit so that you don't have to watch me writing all of that out. So I'll pick you up after I've done a bit of work on that. Okay, so just see you in a second. Okay, so picking up from where we got up to previously and just explaining what I've done here. Let me just get my pen back here. Okay, so what I've done is I've taken this expression we had here, written it out, and now I'm multiplying by the conjugate of the bottom part. So cos A plus I sine B is simply a complex number in polar form. Its conjugate would be this here, cos B minus sine B. Okay, so multiplying top and bottom by that, multiplying this out, cos A times cos B, cos A times negative I sine B would give this here. Okay, and then we've got, sorry, get rid of that damn message. Okay, where do we get up to? We got I sine A times cos B, which is this one here, and I sine A times negative I sine B would be minus I squared sine A sine B. The bottom line, we get cos B times cos B. Now that would be cos B all squared, but you write it, the typical way in which that is written is cos B squared B, I should say. So trying to make that a little clearer. Yes, that is equal to the cosine of B all squared, but the way that mathematicians write that is this, cos squared B, and it means this. So why do we write it like this one here and not this? Because it's a shorthand form, means we don't have to put the brackets in. Okay, so where are we up to? Well, you might notice that those two cancel, and let's take that top line and once again let's group together the real parts and imaginary parts separately. Just move that up a bit, slightly more if I can. No, not that far. There we go, that'll do. Okay, so what are we going to get? We're going to get cos A cos B Now I squared is equal to negative 1, so minus negative 1 becomes plus 1, so plus sine A sine B, and then this part here, the imaginary bits, let's take I out as a common factor, and I'm going to put the positive term first, so sine A cos B, and then this negative term here, so minus cos A sine B. Okay, a big bracket, and let's divide. Now what are we going to do on the bottom? Okay, these parts have cancelled. Now I'm going to take this A term first. Now I squared is equal to negative 1, so minus negative 1 again, positive 1, so sine squared A, and we've got a positive cos squared B. Why have we got B for? That's going to be a little confusing. Hold on. Don't know where that A came from. That was an error. So let me just get rid of that, because I'm multiplying sine B times sine B. That should have been sine squared B. Let's move this down a fraction again if I can. Okay, so bottom line would be sine squared B plus cos squared B. Okay, so what does this all equal? Well, let's take a look at that bottom line first, and we're going to jump back to these trig identities here. This first trig identity says if you've got the sine of an angle and you square it, and you take the cosine of the same angle and you square that, and you add those two parts together, you'll always equal 1. Now you can I'd say prove it, but you can verify that it's certainly working if you put some angles in here. Remember, x has to be the same for both of these. So take an angle in degrees if you like, okay, and take the sine of the angle, square it, take the cosine of the angle, square it, add the two parts together, you should get 1 every time. Okay, so that bottom line here on this work that we got up to at this stage, that equals 1. Now what about the top line? Okay, let's go back to the identities here. We've got cos A cos B, so it looks like this third identity again, plus, now that's the bottom line here, plus sine A sine B. So that matches on the left hand side with cos of A minus B. So that's what I'm going to put in here. Okay, so let's put a bracket. So this part here is the cosine of A minus B, and then the imaginary part, okay, sine A cos B, that looks like the second identity, minus, so that's the bottom line here, cos A sine B. So that matches on the left with sine of A minus B. And so what we have then, we've got that, and remember the bottom line was equal to 1, so let's just simplify this further. That's R1 over R2, and this here is simply a complex number in polar form where the argument is A minus B, so all of this can be replaced with CIS A minus B. Once again, what does that mean? It means that when we are dividing two complex numbers in polar form, we've got Z is equal to R1 CISA, and we're dividing that by another complex number, say W, which is R2 CISB, that the result is this. We're going to divide the two moduli, and we're going to subtract the arguments. So let's take a look at a simple example again. So if we had A is equal to, let's say, 5 root 2 CIS, let's say we had pi over 2, and we've got B is equal to, let's say, what can we make that? Let's say 10 CIS, and we've got pi, let's do something a little larger this time. So it's a bit messy. Let's rewrite that. 10 CIS 5 pi over 4. Okay, so what is A divided by B? Well, that would be 5 root 2 over 10, and the arguments we're going to subtract, so pi over 2 minus 5 pi over 4. Okay, so this will simplify down to root 2 over 2, which can be simplified further, and we'll do that in a moment. CIS now, pi over 2, the common denominator would be 4, so that's going to be 2 pi over 4 minus 5 pi over 4. Let's write it like that. Now what about the moduli? Remember that 2 is equal to root 2 squared. So root 2 over root 2 squared would become 1 over root 2. CIS. And can we have a negative argument? Yes, we can. Okay, and it's going to be negative 3 pi over 4. So what that is, remember, if you have a negative argument, sorry, let's get rid of that. Let me just make that a little easier to write, hopefully. Damn, the angle here, and I can't draw a straight line vertical very easily. Okay, let's try that again. Let's just use that, say, and let's do another line here. Okay, so an angle of negative 3 pi over 4, that's negative 3/4 pi, which actually would be about here. And that's a negative angle, so it's going clockwise, negative 3 pi over 4. And if the modulus was 1 over root 2, that distance from here to here, that distance there, would be 1 over root 2. So the modulus, let's say r, is equal to 1 over root 2. It's meant to be an equal sign. Man, that is terrible. Let's write that again. Okay, so that's the proofs, okay, and the end results are the key things you need to remember. And what you're going to do in class is to do a number of questions based on that. Okay, I'm going to get you to have a look at the examples on page 56, and then try the questions on page 57 and 58. Okay, see you in class.